Welcome back to today's session. Till now, we studied assignment problem, which was a special case of LPP. From today, we are supposed to start off with a newer topic, which is TSP, which is also called traveling salesman problem. This is also a special case of linear programming. If at all you people have enjoyed solving assignment problem, you will enjoy solving traveling salesman problem as well. It is far more easier and far more interesting. So let us have a look at this particular problem. So traveling salesperson problem, or TSP in short. Let me explain this problem first. We have a salesman who is supposed to visit n number of cities. He starts from a particular city, visits each and every city exactly once, and returns back to the city from where he started. Right? He starts from a particular city, visit each city once, and then return back to his starting point. Then what is the objective of this problem? The objective of the problem is to find a sequence of cities which he has to travel, so that his total traveling time, or the total traveling distance, or the traveling cost can be minimized. One basic knowledge that we already have is, if we are supposed to visit n cities, there are n minus 1 possible routes, right? To visit n cities, we will have n minus 1 possible routes for it. So a TSP is a special case, or I can even call it a restricted form of assignment problem. Why restricted form of assignment problem? Because the structure of the assignment problem and the traveling salesman problem is almost the same, except for one difference. Except for one difference. In assignment problem, your principal diagonal element were uh, not restricted. But in a traveling salesperson problem, your principal diagonal elements will always be infinity, because we are not allowing self loop. That means to say, from a city A, he cannot go back to city A, or from a city B, he cannot go back to city B. So this is avoided. Therefore, we assign the values for the principal diagonal as infinity. So that is the only additional restriction. Therefore, I can call TSP as a restricted form of assignment problem. So if at all I can call it as a restricted form of assignment problem, and assignment problem was a special case of LPP, so obviously TSP will also be a special case of LPP. So we call it a restricted form of AP, as all the problem properties are the same except for self loop entries are absent. As I said, principal diagonal elements will not be there. All the principal diagonal elements will be infinity. Right? So now we will have a look at the structure of your TSP. We will see how TSP looks like. So like in AP, here also we have an n cross n matrix, that is a square matrix. We denote this matrix by C. Let C be an n cross n matrix representing the cost, or the time, or the distance for each of the n cities to each of the remaining n minus 1 cities. Why remaining n minus 1 cities? Because self loop will always be infinity. Out of the n destinations, one destination is avoided to us. Remaining n minus 1 cities, we will have a distance, or a cost, or a time for it. Okay. So here we denote these costs, are the matrix entries, as Cij. Cij is the distance or the time or the cost of going from city I to city j. The decision variable, like in assignment problem. In assignment problem, we had the decision variable as xij. If at all there is an assignment, it would be 1. If there is no assignment, then it would be 0. Right? The same thing holds good here also. The decision variable xij will be 1 if the salesman is traveling from city I to j. If he is not traveling from city I to j, then that xij value will be 0. Okay? Since the salesman travels from city I to city j, and we have a restriction there, he can reach the city only once. Right? So if he is going from I to j, he cannot come back from j to I because he would be visiting it for the second time. So that has to be avoided. So since the salesman travels from city I to city j, he cannot travel back from city j to city I. Okay? So this is the structure of your TSP. So mathematically or in form of a matrix, how does it look? We will just have a look there. So this is how your traveling salesperson problems look like. So all your principal diagonal element entries will be infinity. So the number of cities are 5. Then in the source also you will have 1, 2, 3, 4, 5. In the destination also you will have 1, 2, 3, 4, 5. So like in assignment, you cannot have 1, 2, 3, 4, 5 on one side and A, B, C, D, E on the other side. There it was the concept of workers and jobs. Here it is source city and destination city. Whatever is the number of cities specified, that will act both as the source and the destination. Therefore, the row headings and the column headings will always be the same. Fine. Row headings and column headings will be the same. All principal and diagonal elements will be infinity. Rest everything looks like assignment problem only. So whatever is given in form of a graph here, sometimes what happens is in the problem, they might not give you the dabba here. They might give you the diagram. Looking at the diagram, you are supposed to construct the dabba. Okay. So 1 to 1 will be infinity. From 1 to 2, what is the cost? 7. So 1 to 2, 7. 1 to 3 is 9. 1 to 4 is 6. 1 to 5 is 1. Okay. So whether I travel from 1 to 2 or 2 to 1, the path is the same, right? It is an undirected graph. If at all it is an undirected graph, whether I travel from 1 to 2 or 2 to 1, it is the same. So like 1 to 2 was 7, 2 to 1 will be the same line. 2 to 1, 7. 2 to 2, infinity. 2 to 3, 3. 2 to 4 is 4. 2 to 5, 9. 3 to 1, 3 to 1, 9. 3 to 2, 3. 3 to 4, 2. 3 to 5, 5. But 3 to 3 is once again infinity. 4 to 1 will be 6. 4 to 2, 4. 4 to 3, 2. 4 to 4 infinity. 4 to 5, 3. Similarly, 5 to 1, 1. 5 to 2, 9. 5 to 3 is 5. 5 to 4 is 3. 5 to 5 will be infinity. Now you also know if the problem is not directly given in the matrix form, but it is given in a diagrammatic form, you know how to convert it to matrix form also. Right? This is your TSP structure. So once you know how to construct a problem out of the given scenario, we have to look into the mathematical modeling part of it. So given a cost matrix C, the solution for it will be a permutation matrix X. all zeros except for one one in each row and each column. See, like in assignment problem, every row can have one assignment, every column can have a single assignment, right? The same thing holds good here also, because you are supposed to visit every city only once. Therefore, every row has a single assignment, every column has a single assignment. That is what we have written here. Next, the objective of your TSP is to minimize the total cost or the total distance or the total time of traveling. So we denote this total cost as double summation of Cij Xij. Cij is the cost matrix entry. Xij is either 0 or 1 based on whether you are considering that route or not considering that route. Okay. So the actual mathematical formulation of your TSP looks like: minimize z equals double summation of Xij, Cij Xij, subject to the constraints are, as I said, every row can have only one assignment. So single summation of Xij is 1 and single summation of Xij is 1. This is row wise constraint. Every row can have only one assignment. This is column constraint. Every column can have only one assignment. And our basic idea is to find a sequence. UI will be a sequence in which city I is visited. That means to say every city has to be visited. None of the cities can be skipped. And you are supposed to visit every city exactly once, except for the source, because we start from the source and come back to the same starting point. Okay, so that constraint is given as ui minus uj plus n of xij should be less than equal to n minus 1. So this means to say, whenever I am forming a closed path, right, a path starting from city 1, visiting all the n cities exactly once and coming back to city 1 itself, the starting point itself, then the number of edges or the number of lines that I would have drawn will be equal to n minus 1. So I'll just show it to you in the figure here. See, let me say I started with 1. From 1 I went to 2. So how many lines I've drawn? One line. From 2 I go to 3. How many lines I've drawn? 1 to 2, 2 to 3, 2 lines. Then from 3 I go to 4. How many lines I've drawn? 1 to 2, 2 to 3, 3 to 4. 3 lines I've drawn. From 4 I go to 5. How many lines I've drawn? 4 lines. 1 to 2, 2 to 3, 3 to 4, 4 to 5. And from 5 I am going back to 1. See, leave this line, right? Joining back to the source, leave that line. How many more lines I have constructed? 4 lines. How many nodes I had? 5 nodes, right? So if at all you have 5 cities, to travel, the path length will be n minus 1, excepting for or leaving back the uh, path or the route joining back to the source. Leaving that 4 minus, 5 minus 1, 4 lines I would have drawn. That is why I say it should be equal to n minus 1, right? ui minus uj plus n into xij should be less than equal to n minus 1. And then the last line, for all ij belongs to n minus the source. Okay, understood? This is your mathematical formulation. After understanding the mathematical formulation, what next? So do we have categories of problems in TSP? In AP, we had 4 categories of problems, right? Minimization balanced, minimization unbalanced, maximization balanced, maximization unbalanced. A TSP cannot have unbalanced problem. Why it cannot have unbalanced problem? Because the number of cities specified in the problem acts both as source and destination. How many ever sources you will have, the same number of destinations you should have. Because that is a compulsion, there is no chance of unbalanced problem. So out of these four, two went off, right? Out of minimization balanced, minimization unbalanced, maximization balanced, maximization unbalanced, two went off, two with unbalanced went off. So there might be two more categories, right? One is minimization problem, other one is maximization problem. Now we'll see. When the problem is about traveling, the possible decision variables will consider either cost or distance or time. Most of the times, the decision variable will be cost or the distance or the time. So whether I consider cost or whether I consider distance or whether I consider time, my objective will always be minimizing it only, right? In all these cases, it has to be minimized. So only minimization case exists in TSP. So there is only one possible category. Therefore, TSP has only one category, which is the standard type, which is balanced minimization case only. No different categories. Whenever a problem is given, it is understood that it has to be balanced and it has to be minimization type. Okay. So now just let us have a look at the algorithm. See, Hungarian algorithm was used for solving assignment problem. Now I'll modify this Hungarian algorithm a little bit for solving TSP. We call it the modified Hungarian algorithm. So what modifications we have done? Step one. Step one, there was converting maximization to minimization. Then step two was converting unbalanced to balanced. No, those two steps do not exist here at all. So because problems will always be standard type, so step one and step two, which were there in assignment problem, does not hold good here. Straight away we are going into row reduction. So choose the minimum in each and every row and subtract this from the rest in that row. Repeat for all the rows. That is the row reduction step. Step 2, perform column reduction step. Okay. Same like assignment problem. First perform row reduction, then perform column reduction. Check whether all rows and all columns have zeros. If all columns and all rows have zeros, straight away go into the assignment step. That is the step that we have written here. Choose the row or the column which has only one zero, if not two, etc. That is based on the number of assignments that we have, make an allocation for a particular zero. That is putting the dabba. After putting the dabba, cancel all zeros in the same row and same column. Right? In the same row and same column, if at all I have extra zeros, what was I doing? Put a cross mark, cancel it. Right? This process will continue till all possible allocations are made. Right? After all the allocations are made, in assignment problem we had ticking and line drawing. That doesn't exist here. In this case, after doing the allocations, for every allocation made, compute the allocation penalty. So for every dabba that you have drawn, on the dabba you will be writing the penalty. So what is this penalty? It is the sum of the minimum element in the row and the minimum element in the column. So wherever you have put a dabba in that particular row and in that particular column, look for the minimum most element, right? Add those minimum most elements, and that will be the allocation penalty. Okay. So now for all the allocations that you have made, you have calculated the penalties and you have written on the dabba. After doing that, the allocation with the maximum penalty, out of all those penalties that you have calculated, whichever dabba has the biggest penalty, consider that, right? That particular row and that particular column is selected. Row acts as the source, column acts as the destination. So that gives you the route in which you are traveling. Let me say you got an allocation at 3, 2. So third row, second column you got. So you are now traveling from city 3 to city 2. That is what it means. So once you know that you are traveling from 3 to 2, you cannot come back from 2 to 3. So that is what I am doing here. Once you consider the route in the path, then its reverse route is set to infinity. I will write 2 to 3 as infinity. Because from 3 to 2 I have traveled, I cannot travel back from 2 to 3. So 2 to 3 I'll set to infinity. Right? This is your step number 5. Then step 6. Redraw the problem. Wherever you got an allocation, leave that row and leave that particular column. The remaining rows and remaining columns are copied. That is called reframing of the problem. Right? That is step number 6. The corresponding row or the source and the corresponding column, which is the destination, is removed and the problem is reframed. We rewrite the problem, leaving that row and leaving that column. Okay. So once a new problem is obtained, go back to the step 1. If needed, perform row reduction. If needed, perform column reduction. Then make allocations. After making allocations, find out the allocation penalty. After finding the allocation penalty, find the maximum penalty and identify the row and column that will act as the root. Its reverse is set to infinity. Leave that row, leave that column, rewrite the problem. This process is repeated till when? Till all rows and all columns exhaust. For the new problem obtained, repeat the steps until the total path is obtained. Right? Till you have got the total path, you will solve. When do you get the total path? When all rows and all columns are exhaust. That's it. This is the algorithm for TSP. Hope you have understood. You will understand it further more clearly when we solve a problem on this. So in the next session, let us solve a problem. Let us solve a problem or let us solve problems on TSP. So I'll try if I can solve 2 or 3 problems on TSP so that you will understand how the penalties are calculated and how the allocations are considered. So let me see if at all I can solve either 2 or 3 problems. Till then, what are we supposed to do? Stay home, stay safe. Thank you for your patient listening. Bye. Thank you.